study of morphology, luminescence, and dielectric properties of nanoscale Lanthanide phosphonates.
No.
You will have
Hello, my name is Zareba. I am a PhD student at the Professor Marek Samoć research group. Originally, what we do is the experimental nonlinear optics, but today I would like to tell you something different that we usually do. Today I would like to share with you on our studies on morphology, the electric properties and luminescence of nanoscale lanthanide phosphonates. I will begin my presentation from a brief introduction to coordination polymers and metal phosphonates. Then I will present you the material that we repeated and that and which we make the modification of synthesis. Then I will show you the characterization of materials, including TEM studies, powder diffraction, infrared studies. Then I will move to dielectric and luminescence measurements, and then I will sum up. So, for those who are who don't know a lot about coordination polymers, so coordination polymers are like metal complexes, but they have coordination bonds that propagate in 1, 2, or 3 dimensions. Structurally, they are quite similar to organic polymers, but in properties they are very different, because we know that polymers are partially crystalline, they don't have a precise melting temperature, and CPs, coordination polymers, called also MOFs, are systems in which metal ions and ligands interdigitate, and they are definitely crystalline structures. And for construction of coordination polymers, usually are used carboxylic acids, also are used quite commonly endonor bases, but there are research groups that use sulfonic and phosphonic binding groups for that purpose. And phosphonic acids are derivatives of phosphoric acid, in which one oxygen is replaced with carbon, either of aliphatic or of aromatic part. And phosphonic acids have 3 forms: protonated, deprotonated, and bideprotonated. And those 3 protonation states, combined with a variety of coordination modes shown to the right, make the coordination chemistry of phosphonic acids quite unpredictable. There are, however, some general tendencies One of those tendencies is that phosphonic metal phosphonates tend to form layered structures in which there are inorganic layers interdigitating with organic layers, or organic ligands serve as pillar in between metal sheets. Phosphonic acids also show high affinity to metal ions, especially those tri- or tetravalent, and because of high affinity, because of high binding constants, the formation of materials occurs very fast, so the materials are quite often microcrystalline, and the structure can be solved, usually is solved from powder X-ray diffraction or synchrotron diffraction. So the original report on layered lanthanide phosphonates was provided by Clearfield and co-workers in 2011, and they obtained a series of lanthanide phosphonates using hydrothermal convection type reaction, in which they mixed the ligand shown to the left. Ligand shown to the left, and they heated it with lanthanide source for over 5 days, yielding typical layered structure. They have shown that such materials are form microparticles, and that they show very high thermal stability. As for metal organic structure, most of them were decomposing at about started to decompose at about 500 degrees centigrade. Our approach was the exchange of traditional heating in the convection oven, and we replaced it with microwave heating. So we obtained, and microwave heating is known for the fact that usually the materials obtained in this way are smaller. And indeed, we were able to finish the reaction in 5 hours instead of 5 days, and we obtained correspondingly smaller particles. And now I would like to move to our results that we made in the field. Here I've shown the TEM photographs of resulting materials of cerium, lanthanum, neodymium, europium, gadolinium, and terbium metal phosphonates. And we can see that all structures are composed of irregularly shaped flakes that have size of the thickness of about 20 nanometers and the length of about 100 to 200 nanometers, with the exception of lanthanum analog, which tend to form radial superstructures. Using electron dispersive spectroscopy, we determined that our materials do not have any lanthanide impurities, and the only additional ones are copper and silicon. We found that materials decompose under electron beam, hence the diffraction pattern that we try to obtain is not sharp. XRD characterization has shown that, as we can see, the spectral features are broadened, which is expected for nanoscale material. And indeed, the materials are isomorphous and correspond to the earlier described phase. The same conclusion can be drawn from the IR characterization, since the spectra between materials are very similar. Here for for the comparison is provided the spectrum of phosphonic of ligand, and we can see that the main spectral change is the lack of phosphoryl group stretching vibration. And now I would like to move to the summary of dielectric properties of nanoscale metal phosphonates. The measurements were conducted in broad temperature range from about -100 degrees to about 300 degrees, and we can see that the main dielectric anomaly is visible during the heating cycle, and by calculation of relaxation energy and based on the temperature of the anomaly, we can say that that it comes from the presence of adsorbed water on the surface. When lowering the temperature during the cooling cycle, the dielectric permittivity is constant throughout the measurement range. Here I am showing the cooling cycles for all our samples. As we can see, the dielectric permittivity vary in the range from 5.2 to 6.1 at 1 kilohertz at room temperature, and the one exception is the lanthanum analog, which dielectric permittivity is about 7.2. We tried to find a dependency of molar mass or ionic radii of lanthanide ion on the dielectric permittivity, but right now we are not able to find any tendency. However, those values are quite small and fall within the range of so-called mid-K dielectrics, and this topic is widely investigated in the field of metal organic frameworks. And finally, here I am showing the luminescent properties of europium and terbium phosphonate nanoparticles. In the previous work, authors told that the lifetime is about 1/4 millisecond and the decay is mono-exponential. In our hands, for smaller materials, we found that the lifetime of europium emission measured at 6 for the strongest transition is shorter and is about 1.1 millisecond. And analogously for the terbium emission at 550 nanometers, also we have noted the bi-exponential decay, also correspondingly small lifetime. To sum up, I have shown you our preliminary results on nanoscale lanthanide phosphonates that we obtained in the microwave method. The morphology was, we have called these nanoflakes. Purity and identity has been established with powder diffraction and other methods. Dielectric studies shown that our materials are mid-K dielectrics, and the dielectric permittivity is flat during the cooling cycle, and the lifetimes of nanoscale europium and terbium phosphonates are smaller or lower than for microcrystalline analogs. The work was funded under Maestro program and also partially from the instrumental grant from Polish Ministry of Science and Education. I would like to thank you for your kind attention.
Thank you, Zareba. Any questions? Please.
I have forgotten to mention that I was using the nitrogen laser 337 nanometer, so I have used the ligands as antennas. antenna.
Any more questions? Thank you once again.
Thank you.